Hi guys, nice to see you again. This is just a quick review over how to make specific mathematical models and general equations. None of what I'm about to go through is new. These are things that we've reviewed earlier in the year, but the reminder might be good to run through the assignment we're going to do today, and it's going to become increasingly more important over the next week or two as we get into some new projects. You guys know that for any graph, if you have a line on the graph, we can use the equation y equals mx plus b, where y is simply the name of the y-axis. The slope is the angle of the line, the steepness of the line, which you can calculate using rise over run, or change in y divided by change in x, times the name of the x-axis, and then the y-intercept, which is where your line crosses the y-axis, is known as your y-intercept. So we can use that format of y equals mx plus b for all different kinds of graphs. But unlike in math, a majority of the time that we use these tools in science, we're dealing with real variables. So we define, instead of just y and x, we define actual things. Like this next graph I have here is for a position versus time graph. So this has an object that starts at a position of 5 meters. It is moving in a positive direction at a constant velocity until it reaches a position of 15 meters 20 seconds later. Now, to build our y equals mx plus b, if we wanted to make this a specific mathematical model, we simply replace the y and x with the name of the y and x axis. The y-axis is position, the x-axis is clock reading, and then we have to go and find the specific slope. Well, we know that the slope is the rise over run. For, in this case, it's the change in y, or change in position, divided by our change in time. And in this case, we went from 5 meters to 15 meters, which is 10 meters, and that took a total time of 20 seconds. And you guys know that 10 divided by 20 is a half, or 0.5 meters per second. So we can take that slope and just put it in here for our slope, 0.5 meters per second. For the y-intercept, we have to, again, take a look and see where the line crosses the y-axis. And again, we get 5 meters. So we have position. The final position is a half a meter per second times the clock reading plus 5 meters. But what's the general equation? The general equation is going to take each of the things we have here and use the symbol for those. Now, we already have position as the symbol for this, and the clock reading is already done. But do you guys remember what the slope of a position versus time graph represented? 0.5 meters per second is the velocity of the object. What is the y-intercept for a position versus time graph? Well, it always tells us the y value when the x value is 0. So in this case, it tells us the position when the time equals 0. Position when time equals 0. And that's our general equation. And just so that we can see a couple other graphs, we've got a velocity versus time graph. So it's that we got maybe a car going 50 meters per second, and it's slowing down. Over the course of 10 seconds, it slows down to 20 meters per second. For this, we're going to need to know what the y-intercept is. We've got 50 meters there. We'll need to know the slope. Now, this is a little more complicated because you have to do a little extra math on a negative slope. It's still rise over run. Change in velocity divided by change in time. But because this is a negative slope, it might benefit us to write out the formula. Final velocity minus the initial velocity divided by our change in time. So our final velocity was 20 meters per second minus the initial velocity of 50 meters per second divided by our change in time, which is 10 seconds minus 0 seconds. Well, 20 minus 50 is negative 30 meters per second divided by 10 seconds. In which case we end up with negative 3 meters per second, or we could say meters per second squared. And we know that the slope of the velocity versus time graph describes how the velocity changes, which we call acceleration. So when we build this specific mathematical model, again, we replace y with the name of the y-axis, the slope with the value in units of the slope. Remember the negative sign. The name x is the name of the x-axis, clock reading, and the y-intercept would be where the line crosses the y-axis, which is 50, and you have to use these units, meters per second. This equation will help us find the velocity at any clock reading along here. And to take this to a general equation, We already have final velocity, we know clock reading, we know that the slope of a velocity versus time graph is acceleration, and we know that the y-intercept for a velocity versus time graph tells us, again, the y value when the x value is 0, so it's the velocity when the clock reading is 0. So we say velocity when the clock reading is 0. And one more. And for our last one today, let's take a look at an acceleration versus 1 over the mass of the system graph. This is actually what we started our online learning with a few weeks ago. We were looking at Newton's second law, and we increased the mass of the system, the acceleration got smaller. We had a inversely proportional relationship, and we had to make acceleration versus 1 over the mass of the system to linearize it. Well, to make our specific mathematical model here, we still take the name of the y-axis, acceleration is equal to the slope, which in this case is 0.5 meters per second squared per 1 over kilograms, times the name of the x-axis, which is 1 over the mass of the system. Now in this case, our y-intercept happens to be 0, so we don't need our plus b. And then we said, hey, what's a general equation for this? We've got acceleration and 1 over the mass of the system over here. But then the question becomes, system, what the heck is the slope of this graph? 0.5 meters per second squared per 1 over kilograms. Well, we figured out that that was about 0.5 newtons, and we said, what did we hold constant in the experiment that was about 0.5 newtons? And you guys said net force, and that gives us our general equation. So we got our specific mathematical model and general equation for this last graph. I hope this quick review was helpful. Keep in mind, if I was going too fast, you can always pause. But again, this is all review stuff from things that you learned earlier in the year. Thanks.